Okay, first of all, there's no official readings for this course, but there are two books, both written by yours truly, that are available from Springer, and they're available. You can get them immediately if you just go online to Amazon or Springer. The electronic ones can be delivered to you immediately, and physical ones within the week or less. Um, or if you want to borrow one from me, that can be arranged. Um, and I will recommend other books as we go along. So if you like to read, you will be well taken care of. And if you don't like to read, you'll also be well taken care of because you don't have to read anything. It'll be just lectures, and the PowerPoint, the lectures themselves and the PowerPoints will be put online and made accessible to you as soon as I figure out how to do that, which is not yet. Okay. The objectives of this course are, as we have here, to understand the earth around us, understand the importance of energy, honor those who helped us understand how energy operates, show the role of energy in natural science in understanding contemporary events, including especially what we call economics, and to help you and ideally our nation prepare for the future. That I think that issues pertaining to energy are likely to be as or more important than issues pertaining to climate, and yet they are just not considered. So what we want to do is make that make that information available and to get this all recorded so that it would be available ultimately to anybody who's so interested. Okay, the focus of the course is the universality of energy and systems. Unfortunately, energy is usually explained to students only as one chapter of their physics course or several, or part of a physics lab, although some disciplines like chemistry and occasionally ecology use a more comprehensive energy approach. But usually in ecology, I'm an ecologist, a systems ecologist, it is considered only in one chapter on what's called trophic or food dynamics, but it's much, much more pervasive. In economics, energy, if it's considered at all, is only a commodity, no different from bananas or coffee or cars or what have you. And we will discuss that in great detail. In fact, energy is part of everything we do. I think about it all the time. In your kitchen, you may think of energy when you boil water, but who thinks of a sharp knife as energy, as a force concentrating device, of cooking as a means of giving the human gut access to plants that have cell walls and are hard to digest, or doing dishes. When I do dishes, I'm always thinking about energy. Energy is in hot water that activates molecules. Energy is in emulsifying agents like your dish soap. Scrubbing is often is obviously physical energy, physical force applied to the food particles. And for me, most importantly, I found out how wonderful Gibbs-free energy is because I can put my dishes in the sink and leave them overnight soaking. And the Gibbs-free energy of the water molecules will remove the food particles so they're easy to clean in the morning and I have to do less. So I like it that way. So I also think about energy and power when I'm riding my bicycle, which I often do on Ashland's bike path. Okay, I'm going to give 8 lectures every Monday at 11 a.m. And the first one, and here they are. And this is also, I sent this out so you don't have to spend any particular time here. And if there are issues that you would like to see covered that I don't cover, then I'd like to hear about it, and I'll see if I can get it in. And I'm leaving the last day open so we can see how this class evolves and what you might be where you might be interested in going. Okay, I'm going to start with a fairly medium lengthy thing about who I am, with an emphasis on how that relates to energy. Here's a picture that was in my hometown newspaper, the Hingham Journal, of me when I'm, I guess, 12 or something, sitting on my favorite stump at my favorite pond, Trip Hammer Pond, in Hingham, Massachusetts. And I never had any issue about what life was about. I hear many young people are having problems with what life is about, but for me, it was always very straightforward. It was about fishing as much as I could, or being in and around and under and in water, and especially the life that lived in water. So I started out that way. I grew up in an idyllic New England small town, except it was bloody cold, on the coast, called Hingham, Massachusetts, 17 miles south of Boston. But it was wild enough when I was a kid that I could ride with holding my shotgun down Main Street of Hingham with my beagle running after me to go look for pheasants, 17 miles from Boston. Now, I can hardly get across the street these days, but when I was growing up, it was really nice. Here I am a little bit older with my dog Timmy along the coast again, fishing, freshwater, saltwater, whatever. I was just interested in fishing and fish. And my father gave me a little turquoise fish, and he said it was so you'd always have a fish with you. Unfortunately, I've lost it. But anyway, he says, you like to eat fish, you like to fish, you like to think about them, you like to study them. So here's a fish for you to have all the time. I went to this lovely college, Colgate, in upstate New York. And the key feature of this picture is the river. It had a trout stream going through the middle of the campus. And this was my dorm up on the 5th floor of East Hall. And I got up the first morning and went down to this creek and caught a 14-inch brown trout, which was a pretty good one in my view in those days, on a dry fly. And I thought, I'm going to be really happy here. And I was. And I went fishing or hunting about every day. And but I also was a fairly serious student, such as I had lots of difficult decisions to make, and I usually went fishing when it came down to that. Now I was an English major, and here's the English building at that time, and this was at that time the biology building, and one cold winter day, somebody said to me, "What are you doing tomorrow?" And I said, "I don't know." And he said, "Well, there's a guy coming and talking about ecology," and this being 1962 or so. I said, "What's that?" And he said, "It's about swamps. You like it." And what it was a graduate of Colgate from many years before, who came back and who had gone to the University of Michigan, got his PhD in ecology. His name was Art Cooper. And he was a professor then at North Carolina State University. And he showed pictures that I can still see in my mind of him and his students out in salt marsh environments, similar to where I grew up, um, hauling nets and taking chemical measurements and so forth, and studying the flow of energy from the salt grass to the little fish and the shrimp and so forth and zooplankton to the fish and ultimately to the fisheries. And I was just fascinated with that. I said, you mean you can do that and make a living? And from that moment, from that hour until this hour, my life has been a straight line, which has mostly been about studying and understanding, attempting to understand aquatic ecosystems. And we'll see a little bit more than that as time went on. So at about age 25, I decided that there were three big things I could do with my life, three things that really interested me. One was become a good ecologist, which I wanted to very much. Second was do a lot of fly fishing. And three, have a family. And I thought long and hard about this. And I decided I could do only two of them well, and I wanted to do it well. And so I opted for one and two. And becoming a good ecologist was very, very hard because I needed to take a whole lot of science because I was originally a literature major. And my last 2 years in college were very difficult because I had to take an awful lot of science, which I'm very glad I did, but it was difficult. But I also like to thank Colgate. It had a really good overview of trying to unite the arts and sciences. And the first book we read was C.P. Snow's Two Cultures. And much of my life subsequently has been, in fact, related to trying to deal with the two cultures in some way. Also, I'm always listening to classical music and opera while I do my science work and so forth. So very pleased to do that. Then I was an undistinguished master's student at Penn State, and then I met this guy. Well, I actually knew him from his paper, H.T. Odom, a really amazing guy, by far the most intelligent person I ever met. I went to Penn State because I took a map of the United States while I was at Colgate, where I was really cold most of the time, and drew a line across the United States of what I thought was the southern distribution of trout streams. And that was Penn State. And then I read some of his papers, and I heard he was at the he just moved to the University of North Carolina, which my mother, a Southerner, told me was a beautiful, beautiful place. And so which is, and so I ended up applying to the University of North Carolina. And this guy has influenced me overwhelmingly in my life, and by far the most brilliant person I ever knew. Great big 6'4" and bright red hair and big smile, and just when you were around him when he's talking, you felt like you were next to a generator. Your hair would stand out, from the induced energy and so forth. That was an amazing guy. But his focus was initially in ecology and later in society, overwhelmingly focused on energy. And what I'm doing in this course is basically trying to bring his ideas, updated by myself, to this class and to this recording. Okay. Here's University of North Carolina, just beautiful place. I was very happy, but mostly I worked. 60 to 80 hours a day. I was really, really interested in ecology and learning to become a scientist. Um, and initially, I was having trouble figuring out what to do my dissertation on. And we had a weekly series of seminars at UNC, and a guy named Peter Larkin, who's a famous salmon biologist, came and gave a talk on salmon, which was at the time most ecology was population ecology. You talk about populations of organisms, of species. And in that night, when we were at the chairman's house for beers, Dr. Odom took me over to the and myself and whoops, I forgot I thought I fixed that spelling mistake. Took me into a corner and said, no one has studied fish migration and that should be systems, from a systems perspective. And bang, I knew I had my idea for my thesis. But then I said, where can I study fish migration? And I went to the coast and I looked at a lot of rivers around, and most of them were too big and kind of overwhelming or polluted. It was just difficult until a friend of mine suggested New Hope Creek, which was perfect. And it was in Duke Forest. Duke and North Carolina have close connections. They're only at 15 miles apart or so. And Duke Forest is in between them. And, this looked like the trout streams of my New England boyhood. And I went back there a year and a half ago, and it was just the most gorgeous, gorgeous place you can imagine. It was fantastic. I felt so happy that I'd been able to do my PhD there. And so here I am. And what I did is, you can see over on the side, this hardware cloth, I put this across the stream and I'd put in two traps with funnels in them. And at that time, it was thought that fish in streams did not migrate, and the focus would be on home range and stuff of that nature. But I found, in fact, the first day I took out my trap, it was full of fish that were moving. And so here's another picture on after rain, so it's a bit muddy. But I found that the fish were moving almost every day, and I eventually made a more sophisticated weir that would block the fish. But over a period of 2.5 years, I studied I caught something like 10,000 fish moving in this little creek. And when I went back and I walked along the edge of the stream, and I'd look in the stream and I couldn't see any fish. And yet I remember seeing them sometimes at night when I was there, but there were these dozens of fish moving every day, and you couldn't see them, but you could catch them. And here is results of 2.5 years. The solid bars are the mass, and the lines are the numbers of fish moving upstream and moving downstream. Downstream is below the line. And you see there's big migrations in the spring, and not much going on in the summer. And so I was just learning to use computers at that time, and a computer plotter. And so I did all kinds of graphing. This is taking individual species of fish, and generally I'd find out that the little guys are going downstream and the big guys are going upstream. So I think I probably didn't catch a lot of the little fish because they were just too little for my device anyway. And I also did 80 times, I studied what's called diel or diurnal oxygen technique in which over 24 hours, I would take oxygen samples and they would go, oxygen in the stream would go up in the daytime due to the photosynthesis of all the plants in the stream and would go down at the night. So you're looking at the production and use of energy in the stream. And I found that the upstream regions in this example had a much larger metabolic activity than downstream areas. And it appeared that fish would move upstream to go to these richer areas for reproduction, where there'd be more food available for the young fish. And then as the fish would get older and larger, they would go downstream where it would be a more suitable habitat for the larger fish, and they would be probably safer from predation there. So that was what my thesis was about. I looked at photosynthesis and respiration over each month of the year in the middle of this graph. And I found two main things: that the big burst of activity in the spring and a secondary one in the fall, and that respiration, that is energy use, is always greater than energy production in this stream. And that's because about half the energy that the stream is using comes from leaves and other detritus, insects coming into the stream and being used by the stream. So this gave me the idea of a energy subsidized ecosystem. At this point, I'm not thinking about human society almost at all, although my advisor was beginning to do so. And then I summarized all of this in what's called an energy flow diagram. And I found out that in terms of energy, the fish that I was most interested in was just a little tiny bit, 1% or so of all the energy being used in the ecosystem. And the amount, I calculated the amount that was used in migration and so forth. And that's a more complicated story, but that's where I got my initial interest in energy. But the important thing is, while I'm sitting out on the rocks of New Hope Creek at night, thinking about what it was that I was doing, I came up with the concept of energy return on investment for an activity, in this case, for fish migration. And it's the energy delivered to society over the energy put into that activity. So I began to think of all of life as energy investments, and natural selection operating only for those that gave a significantly positive energy return on investment. And in my dissertation, I calculated that for every calorie that the fish put into migration, they would get back 5 or so from being able to exploit the richer ecosystems that they migrated to. Now, while I was in graduate school, I was influenced especially by 3 people. The first was my advisor, Howard Odom. Here's another picture of him. Another guy is M. King Hubbard, and then Jay Forrester. And Hubbard was at Shell Oil, and Forrester was at MIT. So from Odom, one thing I got in particular was the incredible importance of fossil fuel energy. And few environmentalists know how to deal with this issue. Well, oil is a bad thing, you know, we spill it and make CO2 and all that kind of stuff. But we're going to look into it and how it means a lot of different things besides just that. So why do we, and this should be in general, not at ESF, this is where I used to teach, why do we focus so much on the environment and so little on resources. If you study ecology, you understand how the fish are completely dependent upon the energy resources of their environment. And we don't think enough about that for our own society. Just to give you an idea of the importance of fossil energy, fossil means old, fossil fuel. In this case, oil, which is our dominant fossil energy. This is a 33 horsepower harvester. And you can see that and this requires 5 people to run it, plus a whole series of stable boys. You've got to fuel your horses, so it requires a lot of the grain production to fuel your I don't know what the ROI of this process is, but it's probably not enormously high. And compare that, this is now 33 horsepower. You can count them, 11 by 3 or something like that. And so you can compare that with a 200 horsepower harvester today, operated by one guy, plus somebody to build this and some oil workers to fuel it. But still, the power that this energy has given us is just amazing. And so, this idea I gained mostly from Odom. I didn't even know what fossil fuel meant before I met him. And here's Jay Forrester. He was the inventor of random access memory, of which he's holding a very early, this is just computer storage, we would call it today. And here's one of the very first of these. And I learned from him you could model a human situation. And he and his students, Donella and Dennis Meadows and Jorgen Randers and William Behrers, wrote this book, The Limits to Growth. Some of you probably seen this graph of looking at from 1900 to 2100, how resources would be used up and the population would increase and till the food per capita would decrease and so forth. So we're going to talk about that a little bit. But that was very influential to me in my graduate and postgraduate training. And then one day when I was browsing in the UNC bookstore, I found this, Resources in Man, back in those earlier days, Resources in People. And in that, I found out about this guy, M. King Hubbard, who I once spent 9 hours with one-on-one. And he was a pretty amazing guy, and we're going to talk about him some too. So those are, he came up with this idea that there'd be peak oil, and the yellow was his prediction back in 1955 for the production in the lower 48 for the United States of conventional oil, and that's the green. And then Alaska has been added in here. Now, this is not up to date, and we're going to, it's changed quite a bit since then, and we're going to talk about that. But anyway, I thought, my God, isn't anybody thinking about this? What are we going to do? So I became involved in various ways with people who worried about the same problem. It was called ASPO, and I think one of you said that they knew me from my ASPO days. So there we go. This was my training and my thought thinking. And so I went on. I kept studying fish migration. And here's a more complicated look at the movement of Alaska sockeye salmon, where there's a pulse of production in the ocean that moves up along the coast with the season, and the little salmon come out at just the right time to nail the zooplankton, the little animals that follow the peak in phytoplankton. That's a whole long story, but I kept working on that and building a computer model of this whole process. But while I was doing this, although I liked my own modeling, ecology at that time was full of theoretical modeling, and I came increasingly to believe that a lot of it was BS. I got really disenchanted with modeling in ecology, and so I took about 8 years off in a way from ecology, although I teaching ecology, and started studying energy. Started studying economics, and after a while, quite a few years, I thought, well, they get Nobel Prize winners. They're smarter than we ecologists are, whatever. And I found out that the models in economics were at least as bad as they were in ecology. And so I thought, what the heck is going on? So what I did personally was I focused on the natural sciences and the resources and the energy stuff that I believed in, and started applying energy return on investment to things like finding oil. And here was my first paper in Science magazine, looking at yield per effort and net energy analysis. Net energy analysis is another name for what we'll talk a lot about, energy return on investment. And so this was my first paper on this, and that was put on the first page of the Wall Street Journal. I remember my brother-in-law saying to me, who was a little bit suspicious and hostile of an ecologist, he said, "My God, you're on the first page of the Wall Street Journal." And he says, "How much do they pay you at Cornell?" And I said, "Oh, about 12,000. He said, 12,000 a month. That's not bad." I said, no, 12,000 a year. You don't go into either professorship or ecology to get rich, I guess. So anyway, then we went on, and I spent, as I said, 7 years studying economics, thinking models would be better and so forth. And it seemed to me that economics as a discipline violated all the principles and laws of natural science that I had just spent a dozen years of hard work learning. So I started applying my natural science to economic issues, wrote papers like this one, again in Science, got lots of papers into the so-called best journals. These Cleveland and Kaufman were my students. Some of you might know Costanza, another student of Odom's, although I revel in it and he barely mentions it. And then I may be the only person ever to be denied tenure at an Ivy League university on the week I had the cover issue of Science. I thought that was kind of interesting. But I'm glad it happened. I have rather mixed emotions about my 13 years at Cornell. So I went on and fortunately recovered, went to the University of Montana, and then the College of Environmental Science and Forestry in Syracuse, where I was very happy. So let's start with what is energy? And first, a few words from science we need to be able to use. Empirical means gathered with your senses, that you count them, you measure them, you understand them through your senses. And it's usually considered to be more correct, but it may or may not be, because our senses can deceive us. But mostly we like to think of empirical as being whatever truth is. Truth, we might discuss that at some point. Theoretical is it's how we think it is without necessarily having proof of it. It's how it should be according to what we think are the fundamental properties of what we're looking at. And to discuss these words in their fullness would take a lot more time. First principles are things we think we know for sure. The laws of thermodynamics, the laws of conservation of energy, and so forth. Validation means to look at your theory or your model against empirical information, usually, and against first principles to see if it's correct, such as we're able to tell. So those are words that we will use sometimes. Well, what is energy? What is energy? We don't know. We really don't know at the heart of hearts what it is, but we sort of know because we know its effects. Energy is defined as the ability to do work, which is the ability to exert a force causing displacement of an object. If something moves, energy must be involved. Despite the confusing definition, its meaning is very simple. Energy is the force that causes things to move. And it's divided into two types. Potential, it's actually, it has the possibility of moving, in kinetic or making movement. In kinetic, it actually moves. We know it makes radiation. We know its forms as radiation, pressure, sound, heat, and so forth. We know the sun provides us with a lot of it. And one way to think about it, there's free energy. That means energy that can do work. And it comes from the sun, and now it can come from other places as well, but it comes from the sun, and it's being degraded to low temperature gradient energy unavailable for work. Okay. Now, it just is. The sun is burning itself out. It'll take a long time, but it's doing that. Now, life, for example, or many other processes intercept some of that and use it. And it's very big and very important to us. But we just are able to intercept it. We can't influence its source or its ultimate degradation. And some people, not me, worry about the death of the universe. So we're going to talk next time about the Big Bang and where did this free energy come from and so forth. But what is energy? I don't know, but you can sure feel it. Get out in a good sunny day at noon. Now, think about our ancestors. What did they know about energy? What did people in the past know about energy? Well, in a practical sense, a lot. Now, here's a fire. Here's a bow and arrow. And the important thing about a bow and arrow is a spear point or an arrow point, which allows this much force to be concentrated into a very small point where it can do a great deal of work. It's a force multiplying mechanism. So if you try to penetrate the hide of this animal with your fist, you can't do it. But if you take the same force and put it in a knife blade or an arrowhead, you can. So people understood this in a practical way, although they probably had no clue what was going on more generally. When we became, quote unquote, civilized, we had new ways to think about energy. And you look at a lot of the gods, Ra and Zeus and Vulcan at his forge. I missed the picture here, and Prometheus. Many of the ancient gods were about energy. People didn't understand how all this might be connected. Well, at that as civilization evolved, we also had the evolution of men and women of science. And I'm going to focus on the ones that were most important to energy. First was the idea of science as prediction. Mostly people thought things happened due to the whims of the gods. But in fact, this fellow Claudius Ptolemy, who was Sicilian living in Egypt, as I understand it, and there were Ptolemies who were rulers in Egypt that were related. And he was a really, really good mathematician. And he was very intrigued with the motion of the planets. And the really curious thing is if you watch Venus, the evening and morning star, if you watch it over time, it normally will go, I don't know which way we're going here, from, let's say, from right to left, but occasionally it backtracks. It's called retrogressive motion, and Mercury will do that too. And how could this be? And Ptolemy figured, well, here's the Earth at X, and the moon at the black blob, I guess. And Venus and also Mercury were going in epicycles. And he was a good enough mathematician to explain and predict this almost perfectly from mathematics alone. So this will be interesting to us later when we look at economics. For certain conditions, the model makes the correct predictions, even though its essence, its theory, if you will, is incorrect. So we know now that Venus certainly does not travel in epicycles, but how do you figure that out? Well, I found this a really marvelous book. And it's Tycho Brahe, this fellow on the top, who was a Danish nobleman, and Johannes Nicholas Copernicus, who was a regular type fellow from Poland or that area at the time. And Brahe was a nobleman, had a lot of money, and he did what a number of people did back then. They built very elaborate buildings to study the universe. So he's looking through a hole in the side of his building, and it was able to very accurately judge where the different planets were over time. And he could measure it on this building size quarter quadrant of a circle. And he had terrific eyesight and spent his whole life gathering data, but he couldn't make sense of it. And he believed that the Earth was the center of the universe and the sun went around the universe, something called heliocentric, which Ptolemy also believed. Kepler just was itching to get his hands on Kepler's data. And finally, in the last months of Brahe's life, he allowed Kepler to get his data, and Kepler was able to figure out how to do it in the back of this book. You have to pretty carefully, you can see how Copernicus was able to do it. And he came up with his 3 laws of planetary motion, and fundamentally that the planets would go around the sun in ellipses with the sun at one foci. And this got those who believed into trouble with the Catholic Church, because God was perfect and God would make sure things would go in circles were perfect. We can't imagine that anybody cared back then, but they did. And so Galileo, for example, got into trouble. He believed very much in Kepler. But Kepler was able for the first time to, and Galileo supported him a century later, to say very clearly that the Earth is not the center of the universe, that the sun is. And this was really, really important, that we could understand things through science, through very comprehensive, detailed observations and thinking about it a lot. And how do you do that? Well, that's a subject of other courses, I suppose. We'll touch upon it. Now, in terms of energy, Isaac Newton was the first person to show that three laws of motion, which were related to energy, to force. F equals ma, the first law of motion. The force is equal to the mass times the acceleration and various manifestations of that. The third one, which you know if you've tried to step into a boat at a dock and the boat goes in one way, and as you push your foot the other way and you fall in the drink. I'm sorry, the first law of motion is that something in motion will stay in that state of motion, can include rest, unless outside force operates on it. The second is F equals ma, and third is every action generates a reaction. But these are incredibly important, and it's interesting, there hasn't been a fourth law of motion derived in the last 400 years. Newton was really an amazing guy. And he also came up with the law of universal gravitation, which incidentally works at the level of atoms in chemistry. You can use it to be able to understand chemistry much better. And so that the force attracting two particles depends upon their mass and the distance between them squared. The two masses multiplied, divided by the distance between them squared. And it can be a little bit more complicated than that, of course, but that's fundamentally what also Newton figured out. And he also figured out light was composed of different colors and other things. Amazing guy. So science was progressing a bit, but our knowledge of energy in 1800 was extremely confused. Heat was thought to be a substance, phlogiston, that flowed from hot objects to cold ones. Meanwhile, even though people didn't fully understand it, people began to make steam engine. Here's Newcomen's first steam engine. And these are big things. And they're really important to pump water out of coal mines. And so you see Newcomen's engine, he pushed steam. Here's the fire at the bottom. And the pink is steam going up and pushing the piston up. And then he'd close that valve, the green one, and open the red valve and put in cold water, and the atmosphere would push the piston back down. And on the other side of the rocker arm would lift up a pump, lift water up out of the mine. And these cumbersome, terribly inefficient things saved England's coal mines, or many of them at that time. But it was terribly inefficient because you were using most of the steam to reheat the piston and the cylinder. And then Watt came along and invented the Watt steam. James Watt invented the Watt steam engine, in which you would have steam come in the top and go out the bottom, and then you'd switch the function with this back and forth lever so that you'd have steam on one side and exiting on the other, and then the opposite, the steam come in the other side and the steam exit on this side. And this allowed the piston to go back and forth. And most importantly, it greatly improved the efficiency. It took far less coal to run Newton's steam engine, even though it was only about, the Watt steam engine, even though it was only 1 or 2% efficient, it was much more efficient than Newcomen's. And then this was applied in all kinds of different ways to railways and so forth. but we still didn't understand energy. So the first step was made by Benjamin Thompson, Count Rumford. And at that time, you'd make a cannon, which had to be a solid piece of metal so they didn't blow apart, and you drill it. This is a drill here, which would generate an enormous amount of heat, which would be cooled with water. And so what Thompson did was he put the cannon in a big tub of water. He dulled the drill so it wouldn't make a hole. It would just go round and round. The energy to run this, incidentally, is by 4 horses walking in a circle.
Jeez.
And they drilled this, put this in a tub of water, and he'd run the thing for days, and the water would keep boiling. So he came up with the idea that heat was not phlogiston, because the phlogiston was not being depleted, kept happening, and began to lead to an understanding of heat as molecular motion. Hotter objects, molecules, and he didn't know what molecules were then, were moving faster. And the most important to come along is this guy, Sadi Carnot, a French military engineer. And he found out it was not heat that was needed, but a gradient in heat. In his book, he had published a little book. He only made 100 copies. Only one of them seemed to have been found, and it was in a bookstall along the Parisian Seine. Somebody found it and gave us ultimately the laws of thermodynamics. And here's a wonderful book called, I don't know how to get this on here right, Einstein's Fridge by Paul Sen. And it's a very interesting, accessible book about what I'm talking about right now. Then James Prescott Joule, and Joule is our unit of energy these days, was a brewer. He was not a nobleman at all. He was not educated particularly, except he was very clever. And he made this basic machine in which you crank a weight. The weight is over here on the right, up a pulley, and you drop it a meter, and it would turn this crank and turn this paddle wheel. And the paddle wheel would make the water increase in temperature. And he found out, it's called the mechanical equivalent of heat, but it's actually the heat equivalent of mechanical work. And he began understanding the process that heat and mechanical work were related in some way. And then along came William Thomson, Lord Kelvin, and he listened to Joule and took him seriously and thought about it a lot, and eventually came up with the laws of thermodynamics, along with some other people. So we end up with the laws of thermodynamics. The first law of thermodynamics is the quantity of energy is conserved. And the second law of thermodynamics is, however, the quality of energy is not conserved. Some energy is lost to low-grade heat at each transformation. So it was very important to understand the difference between high-grade, high-temperature heat that could do work and low-grade heat, meaning heat that's close to the temperature of the environment, from which it's extremely difficult and ultimately impossible to do heat. And this is why it's underlying the fact that the amount of heat necessary to run, or the amount of energy to operate an economy, is not unlimited. And so Thomson was able to write on the dynamical theory of heat. And here we are today. And these scientists, Maxwell, Faraday, and even Steinmetz and others, were understand the relation between energy and magnetism. And then there was Einstein, who gave us a different, not entirely different, but a larger view of energy that I'm not going to discuss here. And here we are now, and I want to take this basic information and use it to help you understand why we want to roll this boulder of neoclassical economics down the hill. So at this point, this is the end of this lecture. My gosh, almost perfectly on the hour. We're going to take a 5-minute break, and then I hope you're going to have some questions for me. And what you better have some questions for me. And I'm going to stop my sharing. And you can now take a 5-minute break. And then if you want to speak, raise your hand. And I sure hope somebody raises their hand. Okay, I'm an old man. I need to take a break. So be right back. Hi, Paul Kemp. Paul was my student 50 years ago. Oh, and his wife. Hi. Hi.
I'm Linda.
Yeah.
Linda, hi. We'll
I'm
get your
his
face
better
closer.
half.
Yeah.
We
I
met
remember a
at
wonderful meal with you.
Yes, at
exactly.
Cajun restaurant.
Yes, it was lovely. All right, I'm going to
Yeah.
leave you to very important matters.
Yeah. Yes.
Are you still living in Louisiana?
Oh yeah, we're in Baton Rouge. In fact, we're probably in the same house. Did we have two boys then? Do you remember?
Probably. I don't remember.
Okay, because yeah, our second one was born. We've owned this house for 30 since 1990. So yeah, I think we're in the same house.
33 years.
We love it.
Yeah. Well,
Except we're afraid of hurricanes, tornadoes, and floods, but other than that.
Yeah.
Yeah,
Well,
but the birds are incredible. Paul was in charge of the Audubon activities in Louisiana. So
yeah, okay.
I'm so proud of him. He's one of my many very successful students. And here he is again.
Well, I
Thank
thought this
you.
was a wonderful opportunity to kind of close the loop. And I know John will be on other sessions. John Day, that is,
Yeah.
who was a PhD student with you, I guess,
Oh,
under
my
H.T.
goodness.
Yoder. Yeah.
And I shall let you continue because I'm having a late lunch and I don't want to interfere with y'all's talk.
Yeah.
And my hair is probably longer, COVID.
It's lovely to hear somebody from Louisiana.
Actually, I'm from Mississippi.
Oh, excuse me.
Yes, really. Okay.
Okay, so let's turn on again. I like it when I can see you because I feel like we have a class, but it's up to you. And I understand if you don't want to use your real name, you can do that and or anything else. But let's nobody's raising their hand. Oh, does anybody volunteer to be my co-coordinator? Which is pretty simple, but it's lets me focus on things a bit.
Well, can you hear me?
Yeah, Laurel.
Okay,
Yes?
I don't volunteer for that, but I do have a question.
Yes. Well, do everybody take a look down at the chat box and click on the chat box. No, that's not what you want to do. Reactions. And you if you click on that, there's a something that calls raise hand. Y'all see reactions on
Raise
the
hand.
bottom or top, depending on what you are. And so, Laurel, why don't you try raising your hand? This is what we want to do. No, down.
I don't see any of those.
Okay, well, you can
terms.
raise your hand either way. Go ahead.
Okay. This isn't exactly a question, but maybe for you to comment on something you said concerning James Jewell. Is that how you
Yes.
pronounce his name?
Jewell.
I just took a note. Did you say Jewell?
Yule, yeah.
Yule. Okay.
Jewel. No, not Yule, Jewel. Not
Jewel.
pronounced as if you're a Scandinavian, but as if you're English, I guess. Jewel.
Okay. Got
Which he
it.
was.
Good. So I just found this statement intriguing. I took a note, heat equivalent of mechanical. And that concept or just that thought that that you think of heat as energy. So what if you could elaborate a little bit about what that means? Are you talking about converting one kind of energy into another, but you also use the word equivalent to? So what were you referring to there?
That's actually a really good question. I hate it when people say that's a really good question.
I know, because you don't know if they really mean it and trying to be polite.
Yeah,
or
but I mean it now. So also, as I told you, we don't really know what energy is at the most basic level. And perhaps we could discuss that sometime if you want, but I'm not sure I'm going to be very helpful. But we do know this, all energy can be converted 100% to heat. I think there's no question about that.
Okay.
And so it's very confusing to a consumer because you get your gas bill in therms and you get your gasoline in gallons, and some things are in your electricity in kilocalories, but they're all interconvertible. And in fact, I have this lovely little program. It's called Convert. And if any of you are interested in actually doing quantitative assessment, you can get this program for free. Some physicist wrote it. And so what all of them are interconvertible in that all of them can be converted 100% to heat. Okay. And so if you want to know how much energy is in a liter of fuel, you burn it and capture all the heat and use it to raise the temperature of water. But we also speak of energy as having different qualities. Electricity has different qualities from simply heat. So you can use heat to you can use electricity to make heat in what's called a resistance heater or a toaster. You just run it through a thin wire and it's hard for the electrons to go through and they heat. but it's not an efficient use of electricity for most uses because you can do higher quality things with it, such as heat a light bulb or run a computer or something like that. Well, the discussions and arguments about this are endless. And in fact, in my own professional life now, I am very much engaged in big arguments about how one should evaluate the electricity from a solar panel. And incidentally, I just put 31 of the bloody things on my roof to run a heat pump. And how should you evaluate the electricity from a solar panel versus the energy in a barrel of oil? And I'm taking up an enormous amount of my time, the intricacies of that argument. But all I can tell you, Laurel, is we can convert them all to heat, and yet each of them have different qualities depending on how we want to use them. Now, physicists like to use the word exergy, and exergy is the useful energy in some source. So if you take a barrel of oil and you burn it in the most efficient gasoline or diesel engine, you only get 20 to 30% of the energy back.
Wow.
So the exergy would be that, and I'm not, some physicists would be angry with me for not being more precise, but you only get some 20 or 30% of that energy as useful work, and that's called exergy. Now, I'm not sure I've answered your question, but I've done the best I can for a first pass.
Great. Thank you.
Would
Thank
somebody
you.
else like to raise their hand, or either computer-wise or
What about
literally? Yes, Paul.
fusion?
What about it?
Well, how do you convert that to heat? Or
Well, I'm going to tell you two stories about fusion. Number one, the most recent, they recently ran a tokamak fusion device, and they got what's called energy break even, and apparently it was enough energy to heat a cup of coffee. And what they would do is they took a little pea-size unit of mass of tritium and deuterium, whatever it is, and blast it with lasers, and they said they made energy break even, which meant that the energy they got out of the operation was as great as the energy that they used to, I guess, confine it magnetically. But then if you the calculation of how much energy it took to make the electricity to make the fusion beams, and the energy return on investment went down from 1 to 1, which is energy break even, to something like get back 1 for 1,000 invested. And then I did a rough calculation of how much energy it took to make the fusion machine, and which is $1 billion or $500 million, and how much energy that was roughly equivalent to, and it was like 1 in 10 to the 9th return for 1 invested. It was pretty low, and so that is. I was invited to give a lecture on energy return on investment at the Princeton tokamak a year ago, 4 years ago, 5 years ago. Pretty big honor, I might add. And I had lunch with the director, and he told me, I said, well, back when I was at Brookhaven, they said fusion would be available in commercial fusion in 30 years. And I said, we've been hearing that for 50 years, still 30 years in the future. And he told me, well, to tell you honestly, says, I think we're going to be able to build one positive net energy fusion device that actually works and delivers electricity to the grid. He said, but I don't think we'll build two. They're too expensive. So don't hold your breath.
Yeah.
Um,
But I wonder why it took so long to understand how inefficient that really was.
because honestly, because we haven't been trained as you were trained to think in a systems perspective. Mostly science goes forward by taking a complex problem and putting it into a box. You hear about test and control. And so you've got to have very carefully arranged conditions so your test is the same as a control, except for the one thing you're measuring. And that usually requires artificial, and it is a mindset that is different from how you've been trained, both by myself and John, to think in a systems perspective. So even though it may seem like a very straightforward, even trivial thing to think in terms of a systems perspective, it's not being done even by those who are operating the tokamak. I mean, maybe they are and we don't know about it, but I don't think they talk about it, because if they did, nobody'd fund them next year.
Yeah.
Yeah.
Thank you.
Okay. Another question, please.
You have a hand raised.
Yeah, okay. Charles, I have one.
Oh,
This is
hi,
Ray.
Ray, yes.
Just a comment on Hubbard's peak oil chart. I guess that all changed when shale fracking was invented, especially for
Yep.
the lower 48.
Yep.
I know it's too early to tell where you're going with this course, but I'm wondering if some of your views, how do they compare? Have you read Vaclav Smil's books at
Oh,
all?
yeah.
I just
I
wonder
know
what
him
you.
pretty well
Oh, you do? Okay.
and
I just
admire
finished.
him enormously. You want to learn
Okay.
about anything, read Smil.
Yeah, I just finished his book, The Way the World Works, and basically understanding that we've developed our society where we need to use large amounts of energy. And I'm wondering where your course is going to go and how we deal with carbon emissions and still have the ability to use these large amounts of energy. It seems like I think his main thing was that it's going to take some time because energy changes are very slow.
Okay, that's a safe answer. Yes, we will talk about that, and I will. First of all, I will certainly admit I was wrong about fracking, and I'm going to tell you, if it wasn't for fracking, we'd be totally screwed right now. Russia would have us by the cojones, and there would be no other possibility. Can we make this transition? I'm still very active in research, and I deal with this question every day. And if you want a simple answer from me, I cannot give it to you. And the answer is maybe. Let's give it a shot. But the political environment of the United States would make this very, very difficult. For not just the obvious reasons. And we will talk about that.
Great, thanks.
These are fun questions. Give me some more.
I have one more real quick.
Yes.
Here I am. You say that Einstein's, you're not going to treat that in this course. Why?
Would you like me to?
at least in some way that shows how his theories and the way they've panned out in practice in the ensuing century plus has to do with the way the stuff that you're teaching in this class, you know, based on what science has come up with,
Well,
at least to that extent. Or why is it so different from what you're saying, what you're wanting to get across?
Einstein himself never refuted, I'm pretty sure. Now I want to say that I am not an expert at all on Einstein, but I read what I can on Einstein and try to understand, but I certainly have not been trained as a graduate student or anything to, and I mean, he's amazing, and we have to accept that he's right, because I understand that our communication satellites are moving fast enough, so you have to correct for Einstein's relativity
Okay.
for you to intercept the signal or to communicate with the satellite. So, but Einstein's issues, as I understand it, only operate when things are moving at a very rapid speed, differential speeds. And everything on the Earth, as we'll discuss next time, is moving along with the same momentum. You are moving at the same momentum as Earth rotating. And if Earth stopped rotating, you crash into the wall at a great speed, because you have this momentum. It's like my dog who likes to travel in the middle part of our car. When I put on the brakes, he still has the momentum of the car as the car is decelerating. So he starts to lurch forward. So,
Right.
as do I, but the seatbelt keeps me in place. So Einstein, well, Einstein showed, amongst other things, that you can take mass, a little tiny bit of mass, and this is fusion, that the molecules of helium that fuse to form hydrogen in the fusion reaction, the mass when you're done is less than a little bit, tiny bit less than when you started. And that is turned into energy at this enormous, enormous number, speed of light squared. And so, yes, and Einstein's concepts are related to nuclear energy too. Let me think about that. It will be hard to do that, but I'll tell you this. Let me give you an answer that I have got within my last week's or two's reading. That gravity isn't quite as Newton imagined, things being pulled together like this. It's an object, or even light, is bent by the curvature of space-time. Now, I can't tell you what the curvature of space-time looks like, except that it's influenced. So, for example, Earth or the sun, which has a large mass, bends space-time. So that means when a star is directly behind the sun, you can see it because its light gets bent around the sun, as Einstein predicted. And somebody famously went to South America and looked through a telescope during an eclipse and was able to see. So, but it doesn't particularly affect economics day to day.
Oh, okay. Cool. Good answer. No, and plus we have time at the end of the class to pursue some thoughts around that might be raised during the time we're together. So thank you.
Okay, well, I have that we have 5 more minutes. I'd like one more question. How about Randall? Oh, wait, Cassie, did you have a hand up or not? Turn on your microphone.
Yeah, I actually did, because I kind of wanted you to explain about the fracking, going into a little more detail about how severe it was had we not done fracking.
I will show you that in lecture 4, I think.
Okay, great.
Okay,
Yeah,
will that be all
happy.
right? Let me ask you to a class. Do you have any feedback for me? Is this a proper level for everybody? Are you comfortable with the level of presentation? Do you want me to do you have any suggestions or recommendations for me to meet your requirements better than I have done today? Ted, you have,
Well, if you were asking me, no, I did have a question. If all of the other questions are finished,
okay, I will take your question, and then I will take Dennis, I think, was asking a question. Dennis, you're next. But unmute. Okay, Ted. Go ahead, Ted.
it's slightly off topic, but you sort of raised it when you talked about fishing and trout. Have you ever read Richard Bardigan's wonderful book, Trout Fishing in America?
Yes. Yes, and I will give you a quote from that book. When he put an alligator into a frog pond, and he put in the second alligator out into a small alligator out into the frog pond, and the silence was doubled. Remember that? I thought that was one of the funniest things I read. Okay, he also wrote Confederate General from Big Sur.
Yes.
I love these books at a certain time in my life.
And watermelon sugar.
Yeah, I haven't seen that. Okay, Dennis.
No, I was just giving you a thumbs up that I thought the pace of your talk and the content was fine. So you're asking
Okay,
for feedback.
good.
I didn't have a
Yeah.
specific question.
Okay, anybody else want to add anything? Got 2 minutes left, and I'm going to use every bloody one of them.
Uh,
I agree, Charles. I
Oh.
think the presentation was great. Absolutely fascinating. Very good.
I have some
Okay, good. I didn't see
logistical,
who said that, but thank you.
It's Mary Kay.
Mary Kay, thank you.
You bet.
Oh,
I have some logistics. I couldn't see your PowerPoint.
well,
Now,
I'll send it to you
Yeah.
since I have your email, I think.
okay, and then I could just follow along on it.
Yeah.
I
The
couldn't see
basic-
it on my screen.
What kind of computer do you have?
An adequate computer.
Well,
but-
that's strange. But I mean, maybe it has something to do with, you're in Louisiana.
That could be. Well, if you send me the PowerPoint, I'll be in good shape, I think.
All right, good. But I'll try to send you the one before, which obviously is not prepared yet. So
Oh.
I get the general sense, at least from a couple of you, that I'm going at about the right level and the right pace, and we will continue to do that.
Yes.
And
Oh, it's a
the
very nice
topic-
presentation.
Oh, thank you very much.
Well, your screen may be occluded by the powdered sugar off your beignets.
By the powdered sugar off my, no, I'm diabetic. I can't.
No,
eat
Paul's computer, since he
Oh.
can't see the presentation.
What do I need to do?
It's the powdered sugar falling off the beignets
Oh,
onto your screen.
Oh,
yeah, but the beignets are worth it
Yes, I agree.
if you have the right coffee.
Well, hey, go have an oyster po' boy for me, Paul. I think I remember that you're George Paul. Is that correct?
Yes.
Yeah.
Very good.
That's an amazing memory of 50 years ago.
Yes.
I'm going to tell you one last thing, George. Oh, that's probably remember this, but he gave me the greatest compliment I ever had practically as a teacher, because in whatever I was teaching, and we went on a field trip and stopped and had a beer on the way back. That was when New York, when you could have a beer at 18. And I said, well, Paul, what are you taking next year? And he turned to me and he says, what are you teaching? Remember that?
Yeah, that was very true.
And that was marvelous.
Yeah.
So, okay, I'm gonna end unless there's anybody has any problem, and I'm gonna get the PowerPoint to Paul, and I'm going to get the PowerPoint up online and let you know when I do. I've got a learning curve here, and also a recording that I've got to do something with that I don't quite understand. So, okay, nice to see everybody, and we'll see you in 1 week, minus 1.5 hours.
Thank you, Charles.
Thanks, Charles.
Thank
Bye.
you.